Pluto is a distant and secretive planet. However, recent announcements by Neil deGrasse Tyson, a well-known physicist, have brought Pluto back into the spotlight with astonishment. They suggested in Revelation that the world of content that goes viral may be on a short course of action with Neptune. But how might this actually work, and what could be the outcomes of such an event? Is this an occurrence that inspires limitless eccentricity, or is there something else advancing toward a celestial event? Join us as we investigate the possibilities. Pluto, a former planet that was later classified as a dwarf planet, remains an intriguing subject. Recent research focusing on the vast universe suggests that Pluto's orbital position is at risk due to Neptune's distance. Neil deGrasse Tyson and other astrophysicists, including Makaku, are raising concerns about the potential for a dangerous collision between these two celestial bodies, which may pose a significant threat to Earth. But how might Pluto itself be affected by such an event? Pluto's orbit around the Sun is distinct from that of any other planet in our solar system. It takes an incredible 248 years to complete a single orbit. Since its discovery in 1930, Pluto has only completed one full revolution. However, interest in Pluto does not wane simply due to time. Pluto's orbit is defined by its peculiarly elliptical shape, moving in stark contrast to the nearly circular orbits of the major planets. Pluto's inclination and orbit are unique, tilted 17 degrees relative to the ecliptic plane. This means Pluto moves along a significantly skewed path, unlike other planets. This inclination and irregularity add layers of complexity to its orbit. One of the most fascinating aspects of Pluto's orbit is its relationship with Neptune. For about 20 years per orbit, Pluto is actually closer to the Sun than Neptune. This challenges our understanding of planetary motion and raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in gravitational interactions. When Pluto's orbit was first studied, astronomers attempted to determine its unique approach compared to other planets with relatively close orbits. Pluto's orbit is notable for its steep inclination and longitudinal preference. As the mystery deepened, researchers concluded that although Pluto's orbit crosses Neptune's, their interaction is more stable than it appears. Celestial mechanics explains these complexities. The three-body problem in space involves understanding the gravitational interactions between three objects, in this case, the Sun, Pluto, and Neptune. These forces determine how their movements evolve over time. In Pluto's case, its interactions with the Sun and Neptune create a stable orbital pattern. One key factor in Pluto's stability is its non-synchronous libration. This means that even though Pluto crosses Neptune's orbit, it is always about 90 degrees away from Neptune at those points. This spatial separation is crucial in preventing their orbits from merging. Another stabilizing factor is orbital precession, the slow, cyclical shift in Pluto's orbital alignment over time. This ensures that when Pluto is at its closest approach to Neptune, it is actually positioned above or below Neptune's orbital plane, adding an extra layer of protection against collision. This concept, named the VZK oscillation by three scientists, describes how gravitational interactions between the Sun, Pluto, and Neptune impact Pluto's orbital behavior. Despite its irregular orbit, Pluto maintains stability due to these oscillations. While these gravitational forces may seem chaotic, they actually maintain equilibrium. Understanding the three-body problem is essential for grasping how gravitational forces influence planetary movement. In the late 1980s, mathematical simulations demonstrated that, despite its stability over long timescales, Pluto's orbit is ultimately unstable in the very distant future. Minor changes in initial conditions could result in significant differences over time. However, for millennia, Pluto's orbital features have remained relatively balanced. Long-term monitoring of Pluto's orbit helps scientists understand the influence of massive planets like Jupiter and Saturn on Pluto's motion. Neptune's gravitational relationship with Pluto plays a crucial role in its stability. Pluto completes its orbit around the Sun in a 3:2 resonance with Neptune, meaning that for every 3 orbits of Neptune, Pluto completes 2. This resonance helps maintain Pluto's stability. Additionally, Jupiter's immense gravitational force contributes to Pluto's long-term stability. Studies show that Jupiter's gravity is strong enough to keep Pluto's course steady over long periods. In fact, Jupiter, Neptune, and even Saturn work together to ensure Pluto's uninterrupted movement through space, preventing potential collisions. These gravitational forces are essential for maintaining balance in the solar system. Without them, Pluto and other celestial bodies could experience chaotic disruptions, leading to unpredictable cosmic events. Discussions about a potential Pluto-Neptune collision highlight the importance of understanding Pluto's orbit. Pluto's position in the solar system demonstrates that even seemingly unstable orbits can achieve harmony through the complex interplay of gravitational and orbital mechanics. This also underscores the importance of continuous astronomical observation to better understand our universe. Exploring deep space forces us to confront the strange nature of celestial orbits. Pluto serves as a prime example of how seemingly chaotic motion can still follow predictable patterns. The concept of orbital chaos refers to the delicate balance governing a celestial body's long-term path. Even minor adjustments in Pluto's speed or position can significantly alter its orbit over time. Computer simulations have been invaluable in tracking Pluto's trajectory. Using advanced mathematics, scientists can analyze how Pluto, Neptune, and other space objects influence one another. Even small changes can have a profound impact on Pluto's final position. In the late 1980s, simulations revealed a fascinating aspect of Pluto's orbit. Despite its non-synchronous libration and irregular trajectory, it has remained stable for millions of years. However, Pluto's orbit still holds an element of unpredictability. Even a slight variation in its position or velocity could lead to drastic changes over centuries. This unpredictability stems from the gravitational interactions Pluto experiences over time. While its current stability is well documented, even small disruptions, such as the gravitational pull of a passing asteroid or an unexpected shift in Neptune's orbit, could introduce long-term changes. These potential alterations highlight the importance of computational models. By simulating Pluto's motion, scientists can predict various scenarios and assess how different gravitational influences might impact its path. Some models suggest that, in the distant future, Pluto's orbit could shift enough to bring it into closer interactions with Neptune, potentially destabilizing its current trajectory. However, this is unlikely to occur within millions of years. Another intriguing aspect of Pluto's orbit is its connection to the broader dynamics of the Kuiper Belt. This distant region of icy bodies extends beyond Neptune's orbit and is home to numerous objects with similarly eccentric orbits. Pluto, being one of the largest known Kuiper Belt objects, plays a key role in shaping the gravitational environment of this region. Interactions with other trans-Neptunian objects could further influence Pluto's long-term orbital evolution. Despite the challenges of predicting Pluto's exact future, one thing remains clear. Its complex dance with Neptune, Jupiter, and other celestial bodies is a testament to the intricate mechanics governing our solar system. The forces at play ensure that, for the foreseeable future, Pluto remains in a stable yet dynamic state, an ongoing mystery that continues to captivate astronomers. Beyond its orbital mechanics, Pluto's surface and atmospheric conditions also contribute to its enigmatic nature. As Pluto moves along its elliptical orbit, its distance from the Sun varies significantly. This causes dramatic seasonal changes, affecting the thin layers of nitrogen, methane, and carbon monoxide in its atmosphere. At its closest approach to the Sun, Pluto's surface warms slightly, allowing these gases to form a transient atmosphere. As it moves farther away, the atmosphere gradually freezes and settles onto the surface as frost. Recent observations from the New Horizons spacecraft have provided unprecedented insights into Pluto's terrain. The dwarf planet features vast plains of frozen nitrogen, towering mountains made of water ice, and deep canyons that hint at past geological activity. Some regions, like Sputnik Planitia, suggest that Pluto may have once harbored a subsurface ocean, raising fascinating questions about its potential for hosting primitive life in the past. These discoveries only add to Pluto's allure. Once dismissed as an insignificant member of the solar system, Pluto has regained scientific prominence. The intricate interplay between its orbit, atmosphere, and surface conditions makes it one of the most compelling objects of study in modern astronomy. As researchers continue analyzing Pluto's long-term stability and its interactions with Neptune, new questions arise. Could Pluto's orbit shift enough to alter the structure of the Kuiper Belt? What role does Pluto play in the broader gravitational framework of the outer solar system? And, perhaps most intriguingly, could there be other, yet undiscovered celestial bodies exerting subtle influences on Pluto's motion? While we may not have all the answers yet, one thing is certain. Pluto's journey through space remains one of the most fascinating narratives in planetary science. Pluto's chaos lasts a very long time, scales of billions of years. This essentially indicates that Pluto's travel around the Sun has some order, despite its initial chaotic appearance, especially in its capacity to foresee celestial events, particularly those that involve unconventional orbits as big as Pluto's. It combats the inherent erratic nature of planetary motion. However, in the long run, these systems' forecasts frequently contain ambiguities. Mathematical models provide excellent tools for comprehending and anticipating the future behavior of celestial bodies, but they also expose our predictive weaknesses. These models rely heavily on the reliability of the initial conditions. Moreover, even a minor error or distortion can result in drastically different outcomes, making accurate predictions a difficult task. In addition to the haphazard nature of planetary orbits, Pluto's trajectory serves as a reminder of the universe's dynamic and enduring change. Despite significant progress in our understanding of celestial mechanics, Pluto's case highlights how much we are still unaware of. The gravitational impacts of massive planets on Pluto's orbit provide useful insights into the broader aspects of the solar system's dynamics. They illustrate how the presence and location of every planet can substantially impact the stability and direction of other bodies in the system. So why is this important now? Astronomers have expressed concerns about the possibility of a collision between Neptune and Pluto. Despite these worries, complex gravitational forces work to prevent such an event. Neil deGrasse Tyson, a renowned astronomer who played a pivotal role in the development of cosmology, provides unique insight into the mysteries of our solar system, particularly Pluto. Tyson's influence in changing Pluto's designation from a planet to a dwarf planet offers valuable perspectives on celestial classification and the evolving nature of astronomical knowledge. He views this reclassification not as a downgrade, but as an adaptation to our expanding understanding of numerous bodies orbiting our Sun. One of Tyson's key approaches to celestial mechanics is the idea of learning through constant change. The intricate nature of orbits like Pluto's serves as a reminder of how much more we still need to learn about space. These questions continue to fuel scientific curiosity. Although space exploration is exciting, Tyson's confidence and opinions on potential interactions between Pluto and Neptune present a different perspective. Could Pluto collide with Neptune? Or is this simply another instance of confusion in an ever-changing universe? Only time and further research will tell. For now, curiosity continues to drive our exploration of the solar system. Beyond the potential for a Pluto-Neptune collision, an even more intriguing question arises regarding the universe's dynamics. Such an event would challenge conventional understandings of planetary stability. The idea that two celestial bodies with such vastly different properties could meet is both fascinating and disruptive, especially when considering their current relative orbits. Pluto resides in the farthest reaches of the solar system, far from the main planets. Neptune, a gas giant, has a powerful gravitational field. The consequences of a collision between these two bodies would be significant, providing valuable insights into gravitational interactions and the solar system's evolution over time. To examine the dynamics of a potential impact, we must first consider the structure and characteristics of Pluto and Neptune. Pluto is a small, icy world with a surface covered in frozen nitrogen and an atmosphere primarily composed of methane, nitrogen, and carbon monoxide. Neptune, on the other hand, is a massive gas giant primarily composed of hydrogen and helium, with lighter elements in its thick, deep atmosphere. A collision between such distinct celestial bodies would completely alter their structure and behavior, creating an event observable from great distances. What makes this theoretical collision particularly fascinating is the influence of other planetary bodies in our solar system. While Neptune's gravitational pull plays a major role in shaping Pluto's orbit, it is not the only factor at play. Jupiter, the largest planet in the solar system, also exerts a significant gravitational influence. Jupiter's immense mass and strong gravitational field help stabilize Pluto's orbit, preventing it from straying into Saturn's or Neptune's path. Together, these gravitational interactions complicate the outer solar system's dynamics, making a catastrophic collision between Neptune and Pluto highly unlikely.